Today we will talk about the beams. The main difference, actually the difference between the beams and the frame or a truss structure, is in the fact that the beams can be loaded along and are loaded along the length of the element, and because of that they also have the bending moments. So when we solve for the beams, we look also at the reactive moments as well as we look at the bending moments along the length of the beam element. We will get ourselves introduced with the concepts by doing the section 11.2, and this is essentially the interpretation of the problem of 5.8 from the mechanics of materials from the bear. And there we have the one beam which is the I beam in profile, and it has a continuous load of 20 kilonewtons per meter on the left, and then the concentric load of 50 kilonewtons, and we want to see how this beam will behave. So let's start a new part, and we have also given our cross sections. So first thing what we are going to do, we are going to create the geometric model of the beam, and this will be the sketch on a front plane, and you are going to make the units to be the mmgs, millimeters, front plane. And now we will set up the line and the first line that will be everywhere where you place the load, or the load's end and starts, it need to have a break point. It need the line structure need to have a break point. So here we will type in 3000 millimeters. Then we will make another two lines which will be collinear. This line will have a length of a 1000. And then the other line have another length of the 1000. 1000. And this is our simple structural member. Now we are going to make the structural member. We close this sketch and we go and make the structural member. Features, insert, weld width, structural member. It doesn't really matter. Yes. And we will select anything like pipe 21.3, that's fine. Now we select as a one group, we select this line, and this line. Click OK. This will build our structural members. However, in this particular case, we have an I profile. So if I zoom around, I can see that this is just some kind of a pipe, and I'm not very happy with that. So I want to make it into the I profile. So how I do that? We did that before. I open this structural member and right click on a sketch, edit sketch, look straight to it. And now I will build the sketch on a page 211. So if we go to sketch, center line, vertical, center line horizontal, vertical dimension is 349 divided by 2. For those of you that don't have a book, please share a book with your neighbor.
11.2,
the page 221 in my books. What? You right-click structural member, and then you right-click, and then you open the sketch and change the sketch. And 127 divided by 2. This one is 8.5. This one at 5-8 divided by 2. And we have one more definition. Fillet of the radius 10. And the distance between here and the distance between here and here 63.5. Fully defined. Now we mirror this, mirror entities. Mirror about this guy, this line, and now we mirror everything. Okay, we mirror everything, mirror line around here. Okay, and here is our eye profile for the beam. We close the sketch, and as you can see, our structure now became a one beefy eye profile. Let's save this as my first beam analysis, whatever. Okay, so here is my first beam. I'm going to choose the material for this beam. ASTM A36 steel. ASTM A36 steel and apply it. Now I'm going to start creating the study. Going to start making the simulation study by clicking on simulation. Under the study advisor, I will start a new study. and I will choose the static. Click OK. And the beam should be the defined. If I go here, if I click on the properties, I open this guy, it should all be beams. Cut list. Edit definition, it is beam, by default is a beam. And let's check those two. It's beam and another, and it is a beam. That is good. Now, supports. We need to place the supports, so we go to a fixture advisor, fixed geometry. And we are in both. And in a fixed geometry we will use the immovable. And we will click on this point as a immovable. Click OK. And now the other one can move on the x-axis. So we will go to a fixed geometry. And we will use reference geometry. And we will choose that
they can't move across the X?
no, they cannot move. So no, they cannot move across the X. So they can move across the X, but they cannot move across the Z.
Okay.
So if I use the reference geometry, I click for this node now. Here goes the front plane. And now I'm going to constrain it. It cannot move in and out of plane. And it can't rotate in any direction. And it can't rotate in Y and in a Z direction. Can't rotate along the plane direction. Okay, click OK. Now what is the next step? Next step is to set up the external loads. And to set up external loads, we go again to the external loads. And we have now a pressure and a force, and in this case it is a force because we are looking at the linear system. And let's first set up the new one. We will click on a beam. This time we are not looking at the nodal force. We are looking at the beam force. Reference geometry is from top. SI. And it is a normal 2, and what is the per unit of length, what means that it is a distributed force, and it is a 50,000 newtons per meter. You see that it is already there. And we can choose the beam element, joint 8.1 if we... Oh, pardon, no, we should first set up not the per unit of length. We should first set up the normal force. Or doesn't really matter. It really doesn't matter. Select top plane as a reference plane. So let's select the top plane. It's not a 50,000, it's a 20,000 newtons per meter. And we select the top plane here. Actually, it should be a front plane, and then it should be in this direction, and we will choose the I select the structural member. This one should be at the front. Yep, so 4,000. Structural member 1. Not the line. I want to select this. Should be the top plane. Oh no, the front plane. Let me choose the structural element. Okay. Normal to plane 2000, and it looks down, and that's correct. Okay. So we need to click 2 times. So okay, here is our distributed load. Now I want also to define the point load, external load force, and I'm going to say that this is at the point, at the node, at the joint, and the point force will be again, let's say, at the front, and the joint force will be on this joint here. So we need to choose the joint, and again out of plane, and this should be a reverse direction, and the force that is acting there is 50,000 newtons. Now we have our model set up. The next step is to run the analysis. And here are the results. So intuitively it looks correct. If you put like loads like that, it looks like something that will bend that way. So now we right click on the results. We right click on the results, and we want to display the shear force. Edit definition. I don't want that, I want go define beam diagrams. Okay, it is a defined beam diagrams, and it says shear force in direction 1 and direction 2. Here is very important thing. Direction 1 is the longer axis of your profile. It may or may not be an X or Y. If that profile was oriented horizontally, then it will be a force in a horizontal direction. If it is a vertical, it will be in a vertical direction. So shear force in a direction 1, and select beam all, and let's see the shear force diagram. Aha! And this looks pretty correct. Look at this. Here is the shear force diagram. So, those here at the end are what? They're our resistive forces. Those are the forces, reactive forces from the ground, from the support. Here, it starts with whatever was your support, and you will have a moment where the force will be zero. What means that it changed you will have a position where the force will be zero. And the position where the force is zero, where it changed the direction, is actually where it will break. Because that's where you have the maximum moment, maximum bending moment is here. And we will see that in a moment, in a second on a moment diagram. So, and then we have our point force applied here. And if we do the sum of all vertical forces and sum of the moments around the point, we will see that this is actually a correct result. And is consistent with analytical. Now, remember approximately the position where this force was zero. It's here. If I switch this, if I go to a result, and if I go to define beam diagram, if I go to a define beam diagrams, and I choose here moment in direction 2, the moment need to be in the opposite direction. Moment is here, Newton meters and all. How about this? Look where the moment is maximal. Look where the moment is maximum. Where it reached the maximum approximately at the point, well, let's look normal to it. Okay, it is at the point where your force was zero. Actually, that's where the bridge will break. It's not where the maximum force is. Because in a bending structure, the failure mode is from bending. It's not, and we will see very soon in a strength of materials why it is like that. As you can see, those analyses are in many actually aspects simpler than the analysis of truss. Now you should start making your own analysis from the assignments that is on a Talonet, and the process is exactly the same. Use any rectangular profile, doesn't matter which profile it is, because those are all statically determined models. So be sure that you don't use the pipe as a circular pipe, because then you will not have a way, you will have no way to know which is the direction 1 and direction 2. Right, so and in your result, you should cut and paste by outprint screen the moment diagrams and the force diagrams, and also you should also list here the result forces. And let's see, the result forces are here. Update. And here. So in your report for each structure need to have also a result force. Wow, what happened? Did it record it or not? Huh?